Hey everyone, welcome. Today we're diving into one of the most practical tools in your entire stats toolkit, actually applying the normal distribution to solve real-world problems. This is where all that theory, well, it becomes a superpower. So let's start with a classic puzzle, one you might have even thought about yourself. Let's say you're looking at two college applicants. One got a 1400 on the SAT, the other a 32 on the ACT. So which one's better? Right off the bat, it's kind of impossible to say, isn't it? And that gets us right to the heart of the problem. Trying to compare those two scores directly is, well, it's the classic case of comparing apples and oranges. They're measured on totally different scales, they have different average scores, and the way the scores spread out is completely different. Now, to put it in stats terms, here's the deal. Every single set of data that follows that nice bell curve, whether it's test scores or heights or weights, it has its own unique mean, that's our mu, and its own unique standard deviation, our sigma. And it's this uniqueness that makes a direct, fair comparison a no-go. So what do we do? How do we solve this? Well, what we need is a bridge. We need some kind of universal translator that can take a value from any normal distribution and pop it onto one single standard scale so we can finally compare them. And that amazing tool, my friends, is called the z-score. The z-score is so clever because it converts any value into its equivalent on what we call the standard normal distribution. I want you to think of this as the master blueprint for all bell curves. It's always perfectly centered at 0, and its standard deviation is always exactly 1. It's our universal yardstick. And the process, the actual act of converting a value from its original unique distribution onto this universal yardstick, has a name. It's called standardization. And this right here is the absolute key that unlocks our ability to compare totally different things. This little formula, this is what does all the heavy lifting. To get the z-score, you take your value, x, subtract the average of its group, and then you divide the whole thing by the group's standard deviation. What you're left with is a beautiful, simple number that tells you exactly how many standard deviations away from the average your score is. That's it. All right, now that we have our awesome translator, we can use it to travel down two main paths. The first path is when we start with a specific value, like that 1400 on the SAT, and we want to find the probability that goes with it. How rare is that score? How likely is it? When we do this, what we're really doing is calculating the area under the curve. And that area, that's the probability. It lets us answer all kinds of cool questions, like what percentage of people scored below a 1400? Or what's the chance someone scored above a 32? It gives that raw number some real-world context. The process for this is a super clear 4-step journey. First, you state the problem in terms of your value, x. Simple enough. Then you use our formula to standardize it into a z-score. After that, you find the area that matches that z-score. And then, and this is so important, you interpret that result in the context of your original question. Now, the exact method changes just a little bit depending on what you're asking. If you want to know the probability of being less than a value, that's the easiest one. It's a direct lookup. If you want greater than, you just use a little trick called the complement rule, which is just 1 minus the less than probability. And to find the sweet spot between two values, you just find the area for both of them and subtract the smaller one from the bigger one. Easy. Okay, so that was path 1. But what if we flip the whole problem on its head? What if we start with the probability? Like, what score do you need to be in the top 5% of all applicants? And we want to work backwards to find the actual score. Well, that's our second path. This whole reverse journey, it has a technical name, and honestly, it makes perfect sense. It's called an inverse normal calculation, right? Instead of going from a value to a probability, we're using a known probability to work backwards and find the original value. And the procedure is just as straightforward. First, you need to identify the known area to the left of your cutoff point. Second, you find the z-score that matches that area. And finally, you use another formula to unstandardize that z-score, turning it back into your original value, x. And here is that reverse formula. It's really just a simple rearrangement of the first one we saw. To find your value x, you just start with the mean and add the z-score multiplied by the standard deviation. This is what translates that universal z-score back into the specific units you care about, like SAT points or pounds or inches. So when you put it all together, what's the big idea here? What's the takeaway? I want you to think of standardization as your own personal statistical GPS. It's this amazing system that lets you pinpoint any data point on any bell curve and understand exactly where it stands in relation to everything else. And the key here is to see this whole thing as a two-way street. The z-score, that's your universal translator. Path 1 takes you from a specific value to a universal probability. Path 2 takes you from a universal probability right back to a specific value. If you can master traveling both ways down this street, you're golden. And this isn't just some neat trick for a class. Seriously, the ability to standardize variables is one of the most fundamental, most critical skills in all of statistics. It's the foundation for so much of the data analysis that literally shapes our world. So now you have the tool. You have this universal translator that can put SAT scores, housing prices, or even manufacturing defects all on the same level playing field for a truly fair comparison. So the only question left is, what real-world mystery are you going to solve first?